Okay, so today we're going to be starting chapter 29. Chapter 29 is the last chapter that we're going to be covering in this class. So before we start with chapter 29, there's just a few things about the final that I want to go over. So the final is on Wednesday. We're going to do everything exactly the same way we did as during the midterm. It'll be on Zoom. It'll be a Canvas quiz. You'll have a couple multiple choice, a couple short answer. You'll upload your work in the exact same way. So the format and everything will be the same. There is a practice final on Canvas, very similar to what you'll expect on the actual final exam. The formula sheet is up there. And as far as, I've gotten a few questions about is the final cumulative? Sort of. So I don't want to say no, it's not cumulative, because there's no way to test on chapters 27, 28, and 29 without using things from circuits, electricity, electrostatics, right? Even with some of the questions we've seen with calculating the magnetic field between 2-point particles, the question might ask you, well, what's the electric field between these 2-point particles? Now what's the magnetic field? Now what's the total force on these two particles? So it's not cumulative in the sense that I'm not going to test you on anything like any standalone questions from chapter 22 or 23 where it's like, okay, the whole question is just calculating the electric potential or something like that. But it is cumulative in the sense that you still definitely need to know Gauss's law. You still definitely need to know Coulomb's law. You need to know how to calculate the potential energy of some point particles. Like there could very well be a problem where you need to use conservation of energy to solve the problem. So things like that, and we'll see today we're going to be using sort of a variation on Ohm's law again. So obviously you still need to know some basic things from circuits, but there won't be anything from chapter 26. So nothing with like charging and discharging a capacitor. We're done with that. So nothing like that. There won't be any Kirchhoff's law, no resistors in series, no capacitors in series. You'll see today the kind of questions we do that use some of the circuit things, and you've seen enough problems from the homework and what we do in lecture and discussion, what sort of stuff you need from previous chapters. But the exam will explicitly test on chapters 27, 28, and 29. So that will be what the final covers. I highly recommend that, again, to study for the final, you do lecture problems and also make sure you do discussion problems. And again, the best way to study for the final is just to do a lot of problems. Go over the lecture problems, do them multiple times until you're confident that you know how to reproduce those solutions. Same thing with discussion problems. If you have to do them multiple times, do them multiple times. A lot of students will do a problem once and be like, okay, I did it once, now I know how to do that. But then when it comes time for the exam and you're under pressure, it's very easy to then immediately forget how to do that problem. So make sure that you do the problems multiple times so that you sort of develop like a muscle memory when you're solving them. And when you see them on the final, it's sort of like second nature almost. You don't have to really sit there and think about like, oh, how did I solve that problem that one time I did it? And then also, of course, if you have any questions at all, obviously come to my office hours. If you have any questions about like what sort of material from earlier chapters you need to know. So one more thing I would recommend is I posted the practice final and the solutions. What I would recommend is do the practice final like on Friday or Saturday wait until you've seen all of the material that will be covered on the final, and then actually time yourself and try the practice exam and treat it like a true exam. Don't look at the solutions and work through the solutions as you do the problems, because that sort of gives you a false sense of security. When you have the solutions right there and you're not timing yourself, it's, again, very easy to think, okay, I understand all this, when you have the solutions there and you're not on a time, you're not under time pressure. So try to recreate actual exam conditions. You have the solutions and then sort of see how you do. So that's the best way to use the practice exam. Again, don't sort of just like look at the solutions as you work through it. That sort of defeats the purpose of it. Okay, so that being said, let's get started with chapter 29. So chapter 29, we're going to be looking at non-static magnetic and electric fields. So far we've only seen electrostatics and magnetostatics, where our electric field is produced by a static charge distribution and our magnetic fields are produced by a steady current that's not really changing with time. Now we want to think about, well, what happens if our fields are changing with time? So what we're going to see today is that actually a changing magnetic field will induce an electric field, and a changing electric field can induce a magnetic field. So they can act as sources for the other field. So Michael Faraday was sort of the one who discovered a lot of this. So he was doing experiments where he would take a coil and move it over a changing magnetic field, or move a magnet through a coil and see how the current in the coil was affected. So here, if I just have so this is a coil, sort of like a little solenoid here. So it's a current carrying wire wrapped around this solenoid here. And we have an ammeter to show the current. So if I just hold a magnet stationary above this coil, nothing will happen. There's no current flowing through this wire. The magnetic field is just, staying the same. It's just the magnetic field of a bar magnet, and nothing's happening. Now, if I decide to move this magnet anywhere, basically, if I move it at all, if I move it up and down, what you'll see is that will induce a current in this wire, and your ammeter will show some current reading. So just moving this magnet will induce a current in this wire. Now, what if I took another smaller solenoid, basically, with a current running through it? So this little solenoid here has a current running through it, and right now this one does not. If I take this smaller solenoid and basically insert it into this larger solenoid, and that will induce actually a current in the larger solenoid. And then likewise, if I just vary the current, so if I insert this little solenoid into this larger solenoid and leave it there, but then if I vary the current moving through this little solenoid, that will also induce a current in the larger solenoid, because it's changing the magnetic field through this little solenoid. And so that is going to induce a current in this larger solenoid. And we're going to see how this all works today. And so this was also some of the basis for the development of relativity, which we'll talk more about. We'll see a little bit more of that tomorrow. And this is another example where if we actually were able to do an in-person lab, you'll be able to do all these labs yourself and see how the magnetic field and the current changes, but unfortunately we'll have to settle for these pictures. Okay, so before we get into Faraday's law, let's just quickly review the magnetic flux, since that's going to be the basis of our Faraday's law. So remember, the magnetic flux, just like the electric flux, is given by the magnetic field dotted into some area. Now here, this is an open surface, so it will be an open surface, just like a flat sheet, a square. This is open. So we're not looking at any closed surfaces like a sphere or a closed cylinder. We're just looking at open surfaces for this. So if the magnetic field is constant over this open surface, we can just dot the two into each other. We don't have to take an integral of anything because everything's constant. So we'll just dot the magnetic field into the area. And then here we just have some pictures. So if we have our flat sheet, our open surface, and the magnetic field is constant through this sheet, our angle between the area vector and the magnetic field is 0. So our flux will just be B times A, right? There's no cosine here for our dot product, so it's just the magnitudes multiplied together. All right, and then if we have it at an angle, remember, you'll take the cosine of the angle between your two vectors. So this case will just be BA cosine phi. And then if the area and the magnetic field are perpendicular, so here there's no magnetic field going through this surface because the angle between the area vector and the magnetic field is 90, which gives you a cosine of 90 is 0. So there's no magnetic flux lines going through this area, this surface area. Okay, so we're going to be using magnetic flux a lot today. All right, so now let's look at Faraday's law. So Faraday's law states that a changing magnetic flux can produce an EMF. So we're going to have to use EMF from our circuits chapter. So this is what I mean, that there's some amount of cumulativeness to our exam, because we have to remember EMF from our circuits chapter. So we're going to induce an EMF if we have a changing magnetic flux. And that EMF is going to be equal to the negative time derivative of that flux. Now, it's important to note here, remember our flux, if our magnetic field is constant over some area, our magnetic flux is B dotted into A. So since our time derivative is on the flux, that means that if either the magnetic field or the area are changing, that either of those will induce an EMF. So we'll see examples of both, but it's important to remember that it can be the area that's changing as well. It doesn't just have to be the magnetic field in this case. And so this little, this negative sign here is sometimes referred to Lenz's law, but it's really part of Faraday's law. So this whole equation is referred to as Faraday's law. And then the negative sign here just tells us the direction of the EMF, which we'll do all in a second. So this little negative sign here is referred to as Lenz's law sometimes. So Lenz's law just tells us the direction of the induced EMF. And like I said, it's just basically the negative sign in Faraday's law. So the direction of the induced EMF will be such that it opposes the change in flux. So again, we're going to do a bunch of examples with this. But basically, like, nature wants to keep the flux through some area the same. So however nature sort of has to induce an EMF in order to oppose that change in flux, that will be the direction of the induced EMF. So let's see what this means. So if I have here, I just have a wire loop, and there's some magnetic field, you know, the wire loop is placed in some external uniform magnetic field. So I just have some magnetic field going through my wire loop. And then I increase the magnetic field. So I like turn the dial up on my magnetic field, and my magnetic field starts to increase. So it increases now in magnitude, however much, it doesn't matter, but it increases in magnitude. So this increase in magnitude will correspond to an increase in flux, right? Because if my flux is B dot A, and I increase the value of B, that will increase my flux through the area, you know, enclosed by this wire. So my flux has increased. So nature is going to want to induce a magnetic field that's pointing in the opposite direction. So I increase my magnetic field this much. Nature is going to want to oppose that and create a magnetic field in the opposite direction to try to keep this flux the same, this value of flux the same through this loop. So the way that I would induce, or that nature would induce, a magnetic field in the downward direction, we have to think of our right-hand rule. So if we have a magnetic field that's pointing downward, so we want to induce a magnetic field that's pointing downward, our hand has to turn sort of in the clockwise direction here. So what that means is that we want to induce a current and an EMF in that clockwise direction, because if I have a current going through my wire in this direction, that will induce a downward magnetic field. It will create a downward magnetic field to offset this change in B, or this change in flux here. So that's all the negative sign tells you. It just tells you that if your magnetic field has increased, the induced EMF will just be the opposite of that. Now, another way, or another example of this is, let's say I have a wire loop here. Oops. And there's still some uniform magnetic field going through it. So I still have B here. But now let's say I turn my magnetic field down instead. So I actually decrease the magnetic field. So instead now, my magnetic field is smaller in magnitude, like this. So it's decreased from up here. And now my magnetic field, let's say, is half as strong. So that means that the flux through this area has decreased. So what that means now is that my EMF that's induced is going to want to induce a magnetic field that is also in this upward direction, because it wants to try to keep the flux the same. It wants to have the total magnetic field be back up here where it originally was. So it's going to try to induce a magnetic field that is in the same direction as the original magnetic field. So we're going to induce a magnetic field. Oops. So our magnetic field from our external magnetic field is like this. We're going to try to induce a magnetic field to bring it back up here. And the way that you do that, you can use your right hand rule and say, okay, well, if I want my magnetic field to be pointing upward, my thumb is upward, what direction is my hand curling in? What direction does my EMF and my current have to be in? Well, this now is like counterclockwise. So this is going to induce an EMF in this direction, which will cause a current to run in this direction as well. So in this case, if I decrease my magnetic field, right, I decreased it from here down to here, that will cause a current to flow in the counterclockwise direction so that it will induce a magnetic field also in that upward direction. It's trying to oppose the change in flux by supplementing that magnetic field. All right, so let's do a simple example with this. So we have an electromagnet creates a uniform magnetic field that is increasing in magnitude at a rate of 0.02 Tesla per second. The area of the wire in the field is 120 centimeters squared. Find the induced EMF of the loop. Okay, so let's draw a little picture. So we have a wire here, and we have a magnetic field that is increasing. So we have some uniform magnetic field here, and B is increasing. And we want to find the EMF in the loop. So let's write dB dt is 0.02 Tesla per second, because they said the magnetic field is increasing at this rate. So that means the time derivative of our magnetic field is 0.02 Tesla per second. The area of the wire is 120 centimeters squared. So now we want to find the induced EMF in the loop. So the EMF is the time derivative of our flux, where our flux is just B dot A here. Since our magnetic field is constant over our area, we don't have to worry about the integral. So this, let's write as negative dB dt times the area. So our dot product, our area and our magnetic field are parallel, so our dot product, the cosine will just be 1, so we can just multiply the magnitudes together. So the only thing changing here, the area is not changing. We know the time derivative of our magnetic field is 0.02, so the only thing that's changing here, I can just rewrite the time derivative of the flux as the time derivative of the magnetic field times the area. So I can just plug these two things in now. So I have dB dt is 0.02, and my area is 120 centimeters squared, so that's going to be 10 to the negative 2 squared. So then we just plug all of this into our calculator, and this becomes 2.4 times 10 to the negative 4 volts. So EMF, remember, is measured in volts. Okay, so now the negative sign. So I personally sort of just ignore the negative sign in Faraday's law and then just use the right-hand rule to figure out what direction my EMF is in. So I personally think that that is the easier way to do it. So let's just forget our negative sign here, and then we'll just write on our diagram which way is the EMF induced. So if the magnetic field is increasing, right, that means that we're going to want to induce a magnetic field that's going downward, because we want to try to offset that increase in the magnetic field. So if we want to induce a magnetic field that's in the downward direction, we're going to have to have an EMF that is clockwise, right? So I put my thumb in the direction of my induced magnetic field that I want, and then my hand is now going in the clockwise direction. So I'm going to have an EMF induced in this direction. And that's clockwise. So it's fine if you do that on exams, just sort of ignore the negative sign here. I personally think that the negative sign just makes things more confusing. So you can just ignore your negative sign for this, and then just like write either clockwise or counterclockwise, or just draw a picture so it's clear what direction your EMF is being induced in. So that's totally fine. So anyway, so that's how we figure out the direction and the EMF induced in some wire here. So now we have the EMF. So this is the exact same problem. So we still have the change in the magnetic field was 0.02. Now we just have a picture here of our little circuit. So we have our wire loop that has an area of 120 centimeters. And now they're telling us that the total resistance in this loop basically is 5 ohms. So what is the magnitude and direction of the induced current? So we're going to have to use Ohm's law. So remember back from Ohm's law, the EMF was equal to the current times the resistance. So now we have the EMF and we're given the resistance, so we can just find the current. So all we have to do is just, to find the current, we just divide the EMF by the resistance. The EMF we said was 2.4 times 10 to the negative 4. And the resistance is just 5 ohms. So this comes out to 0.048 times 10 to the negative 5 amps. So this is the magnitude of our induced current. And again, we already figured out what direction that was. We want to induce a magnetic field that's going downward. So if we want to induce a magnetic field that's going downward, we said that the induced current and the induced EMF has to be in this direction. So the current and the EMF will be in the same direction. So it's clockwise. And we're viewing that clockwise from above, right? If we look at it from above on top of the wire, this is clockwise. All right, so that's a basic example using Faraday and Lenz's law. Now, let's do another example here. So we have a 500 loop circular wire with a radius of 4 centimeters. So this radius is 4 centimeters. It's placed in between the poles of a large electromagnet. The magnetic field is uniform and makes an angle of 60 degrees with the plane of the coil. So we have our coil here. The area vector is perpendicular to our coil. And the magnetic field decreases at 0.2 Tesla per second. What are the magnitude and direction of the induced EMF? Okay, so the first thing we have to be careful here is when it says the magnetic field is uniform and makes an angle of 60 degrees with the plane of the coil. That's a little bit tricky because the plane of the coil is this, right? The coil, like when it's laid flat, that's the plane of the coil. And so they're telling us that the magnetic field makes an angle of 60 degrees here with our coil. But remember, when we do the flux, we do the area vector, and the area vector is perpendicular to the plane of the coil. So when we do that dot product of B dot A, we actually need this vector, which makes an angle of 30 degrees with the magnetic field. So our magnetic field is here, and our area vector of our coil is in this direction. So we actually have 30 here, not 60 for our cosine. So we have to be careful of that. Okay, so we want to know what is the magnitude and direction of the induced EMF. And the 500 loop circular wire, it's basically sort of like, we just have, imagine just one loop of wire, and then we just put 500 of them on top of each other, and they're very, very thin. So there's like 500 loops here, not just one single loop. So, okay, now we can find the magnitude of the EMF. So we'll write down Faraday's law, where the flux is B dot A. So let's find the flux first. So the flux is going to be BA cosine theta, where that's the angle between them, or I'll call it phi since that's what they call it in this problem, cosine phi. And we said cosine phi was 30 degrees, right? So this is 30 degrees because B and A make an angle of 30 degrees. So, okay, so we have our BA cosine 30, is our flux. And then what about the time derivative? So to find the EMF, we need the negative time derivative of the flux. But in the flux, the area is not changing. The cosine isn't changing. And we know that the magnetic field is changing, right? Because they told us that the magnetic field is decreasing at a rate of 2 Tesla per second. So our magnetic field, or actually let me write this. So dB dt is decreasing, so it's going to be negative 0.2 Tesla per second. So it's our magnetic field that gets that time derivative again. So if we write the equation for our EMF, so in our EMF, it's the negative time derivative of our flux. In our flux, only the magnetic field is decreasing, the area is staying the same, and our cosine is staying the same. Okay, so our EMF, we have negative dB dt, which we said is negative 0.2. So I'll just do plus 0.2 Tesla per second. So let's find the area. So we have the dB dt. Let's find the area of a coil. So it says that the coil has a radius of 4 centimeters. So it will just be pi times 0.04 squared. So that's the area. And then we have a cosine of 30. And then also don't forget that we have 500 coils in here. So we want to actually multiply this whole thing by 500, because when you have multiple coils stacked on top of each other, you have to multiply by the number of coils. So we'll multiply by 500, and then we can just multiply all of this in our calculator, and this comes out to 0.435 volts. So this is the magnitude of our EMF. Now let's find the direction. So we said that the magnetic field was decreasing. So that means that B is getting less strong. So B is decreasing. And let me just write, we had E was equal to 0.435 volts. So if B is decreasing, that means that it's going to want to induce an EMF to supplement that changing magnetic field. So we're going to want to keep our magnetic field as strong as it previously was. So it's going to want to induce a magnetic field that's in the rightward direction. So if we use our right-hand rule, we say, okay, our thumb is pointing rightward. We want a rightward magnetic field. My hand is like coming out of the page at the top and then going back in at the bottom. So if we look at our coil like this, oops. So if we look at our coil like this, that means that up here, the current is coming out of the page, and down here, the current is going into the page. So this is the direction of our EMF. It's coming out and then going back in, because we want our thumb to be in this direction to keep the flux through that coil the same. All right, now we're going to do one more example that's slightly different. So here we have a U-shaped conductor. So we have a conductor here that's in a uniform magnetic field. So the magnetic field is into the page here, because these are X's, mean into the page. We have it into the page. We lay a metal rod. So we put a metal rod with length L across the 2 arms of the conductor to form a circuit. So we have a closed circuit here. And we move it to the right with a constant velocity v. And this actually induces an EMF in this wire loop. So we want to find the magnitude and direction of the resulting EMF. So let's write down our EMF. Okay, so let's find the flux first. Before we need to figure out what's changing, let's find the flux. So the flux through this area, so we're looking at the area enclosed by our circuit here. So this area here is going to be just the magnitude of the magnetic field times whatever the area of that little circuit area is here. But now, so nothing's changing here yet. But now once I start moving this wire to the right, what is changing? My magnetic field is not changing because it said that it's uniform and there's nothing changing about my magnetic field. But what is changing is the area that's enclosed by this circuit. As I move this wire out to here, my area is bigger now. So my area has actually changed. So let's figure out how to sort of write a formula for our changing area. So we have negative d dt. The magnetic field stays the same. And then our area. So let's write our area. We can sort of draw a little coordinates here. So let's say that this side is length L. And then what length is this side? So according to my little coordinate that I drew here, my position of this wire along the x-axis is just some position x. So let's leave it as x for now, and let's call our area, we're just going to call it L times x, where x is just the position of this wire along the x-axis. So now what's changing here? Like we said, our B is not changing, our L is not changing, but our x is changing. So this time derivative falls on this x here. So let's write it this way. And now, what is dx dt? Well, dx dt is velocity. And we have the velocity. So we can just rewrite this as the velocity. And then we just get B times L times the velocity. And that's our induced EMF, or at least the magnitude of our induced EMF is just the magnetic field times the length of this wire times the velocity that you move this little sliding part to the right. And that's the magnitude of our induced EMF. But now what's the direction? So how is my flux changing? Well, as I enclose more and more area as I move this wire to the right, my area is increasing, right? My area is getting bigger and bigger as time goes on. So that means my flux is increasing, and it's increasing into the page because both my magnetic field and my area vector I defined into the page. So that means my magnetic flux is increasing in that direction. So that means that I'm going to want to induce a magnetic flux or a magnetic field that's out of the page to try to offset that increase from the area. So I'm going to want to induce a magnetic field that's out of the page. And again, I can use the right-hand rule. If I want my magnetic field to be out of the page, I put my thumb out of the page, and then my hand is curling in the counterclockwise direction. So my hand is curling in the counterclockwise direction, which they already drew here. So my EMF is going counterclockwise. Okay, so that's a more tricky example where the area is changing. Now let's talk a little bit about what is actually causing this current to flow. Because right now we're sort of treating it like magic almost. We're like, okay, there's a changing magnetic field and then suddenly a current flows. So what is actually causing this current to flow? Now, we remember that a current is made up of moving charges. So if I have, a wire, that means that I have moving electrons in that wire. And if I have charges that are moving in some path, that means that work is being done on them, right? Because they're moving. So it can't be the magnetic field that's really causing this current to flow, because we said already that magnetic fields don't do any work. Since the force is perpendicular to the displacement always by the way we define magnetic field and Lorenz's law, magnetic fields can't do any work. So it's not the magnetic field that's really causing this current to flow. What's actually happening is that the change in magnetic flux is inducing an electric field, and that electric field is then causing those currents to flow. So in my wire, so when I had a wire, a circular wire like this, and I have my little electrons sitting in it, so I have my electrons, and I have some electrons in this wire. If I have a changing magnetic field, so let's say I have a magnetic field in here that's going into the page, and I increase the magnetic field, this change in the magnetic field will create an electric field. So it will actually create an electric field in this direction. So I will actually have an electric field created sort of in this circular path around inside the wire. And it's also this electric field that's actually doing work on our charges to make them flow. So since this EMF is actually caused by an electric field, we can write it this way. So our EMF is actually given by the line integral of the electric field around this loop. So again, let's say we have a current loop. So let's say we have a current loop, and we have a increasing magnetic field in it. So the magnetic field, the magnetic flux will be given by B times, or B dotted into A. So we'll have B and then pi r squared, whatever that radius of that loop is. So that is our flux over here. Now our E dot dl is just going to be the electric field integrated over this path, which is 2 pi r, because it's just the circumference of our loop here. And the electric field inside it, it's a steady current that's induced inside, so our electric field is constant inside this loop. So this is equal to our EMF. Now there are some very important implications of this. So we said that the induced EMF is equal to the line integral of the electric field around our closed loop. And again, it's very important to note that it's a closed loop because I have that little circle on my integral. So that means it's a closed loop. We're not just looking at some open line. It has to be a closed path. So this immediately implies that the electric field in this case is not conservative. So this is not equal to 0, right? Because we induced some non-zero EMF. So now we can see here that this electric field, when you integrate it around a closed path, you don't get 0. So this is not conservative now. So remember we said when we first looked at the electrostatic force, we said that the electrostatic force is conservative, but that's not generally the case when you have a non-static electric force or an electric field. So when we're looking at these time-varying and time-dependent fields, our electric field and our electric force is no longer conservative. And our electric field does work Q times E to move a charge around the closed loop. So, take a individual charge in our current carrying wire. The electric field that's induced in that wire will do an amount of work Q times the EMF to move that charge around the closed loop in this wire. So we can see now that that electric field is not conservative. So that also means that electric potential has no meaning for non-static electric fields. So we showed in our earlier lecture that if we have a conservative force or a conservative field, that implies the existence of a potential. But now, since we're not dealing with conservative forces and conservative fields, there's no longer a potential. Because when we sort of derived the potential, our whole derivation rested on the fact that the line integral of the electric field around a closed path was 0. So if that's not the case anymore, we don't have a potential anymore because we can't our derivation of it no longer holds. So there's no potential for these non-static electric fields. But this equation, F is equal to QE, this is still true. So the electric force that some particle fields is still equal to that particle's charge times the electric field. So it doesn't matter if this electric field is conservative or not. This is still the force on a particle. So all that's changed is just that this force here is no longer conservative. So just like, we still have the frictional force, even though it's not conservative, it's the same thing here. In the case of electrostatics, this is conservative. In the case of these non-static fields, the same equation is still there, it's just not conservative anymore. So now what this means is that we're going to have to adjust one of our Maxwell's equations a little bit. This was the form of the equation that we used to justify that the electrostatic force was conservative and then derive the potential from that. So that's only the case of static fields. So now when I introduce these time-varying fields, I have to add in this time derivative here. So in the case of the integral form, as we just saw, it is written as the line integral of the electric field around some closed path is equal to the negative change in magnetic flux with respect to t. Then if I want to write it in the differential form, it's just the curl of the electric field is now equal to the negative partial time derivative of the magnetic field. And all this is saying, both of these equations say the same thing. So remember, we just saw the case where we had a wire, and then we said we had some electric field in this wire, right? So we had some electric field present in this wire. So remember, previously for electrostatics, we said that we'd never see an electric field that was curling around something. So now when we have time-varying magnetic fields, we can actually get electric fields that curl around some point. So we can actually get electric fields that curl if we have a changing magnetic field. If we don't have a changing magnetic field, we cannot get electric fields that look like this. And what this means is that you'll never see an electric field that curls around like this, that's going in a circular path. There's no way to create that from static charge distributions. So if we had just like stationary charges, plus Q minus Q somewhere, we would never be able to create an electric field that looks like this. This sort of electric field can only be created by a changing magnetic field. All right, so let's do an example using this new Maxwell's equation. So we have a long solenoid, so that's this here. So we have a long solenoid with 500 turns per meter and a cross-sectional area of 4 centimeters squared. The current in its windings is increasing at 100 amps per second. Find the magnitude of the induced EMF in the wire loop outside the solenoid. So we have this solenoid. We're increasing the current through it, which means we're going to be increasing the magnetic field in the center of the solenoid. And then we have this wire loop just hanging out around the solenoid. So the changing flux through this wire loop due to the increase in current from the solenoid will induce an EMF in this wire. So let's find that EMF. So there's a couple things to write first. So let's just get some of our variables squared away. So it says our solenoid has 500 turns per meter. So remember, for a solenoid, we can write the turns per unit length as lowercase n. So that is 500 turns per meter. The cross-sectional area is 4 centimeters squared. So we can write that as 4 times 10 to the negative 4 meters squared. The current is increasing, so that means di dt is increasing at 100 amps per second. So our current is increasing, and the current is going in this direction. So they tell us our current is coming in through this wire and leaving through that wire. So using the right-hand rule, you can see that the magnetic field is going to be going to the right. So, okay, we want to find now the induced EMF. So our induced EMF It's negative d dt of the magnetic flux. And what is our flux? So it's going to be B times A. So first of all, what is the magnetic field in here? So the only magnetic field that's present inside this wire loop is the magnetic field of the solenoid. And we know the magnetic field of a solenoid. We found that yesterday. So the magnetic field is mu naught N times I. So we found this yesterday using Ampere's law. And this is why I say it's a good idea to just memorize the magnetic field of these situations that we have a lot, like a solenoid, because you don't want to have to sit here and do Ampere's law on a problem like this. You want to just immediately know that the magnetic field is that of a solenoid and just write that down. So I can just write down the magnetic field of a solenoid since we found that yesterday. So this is the magnetic field that's going through here. And now the area. So I have to be a little bit careful with my area because I don't want the whole area of the wire loop, since there's no magnetic field like in a portion of it, right? Up here, there's no magnetic field. I only have a magnetic field inside the solenoid. So I only want to multiply by the area that has that magnetic field. So that's just going to be the cross-sectional area of my solenoid, which they told me was 4 centimeters squared. So I'm just going to multiply by that 4 times 10 to the negative 4 meters squared. So that's my flux now. So you don't want to take into account portions of your wire loop here that don't have a magnetic field through them, since that doesn't contribute to the flux. So, all right, now I have my flux. But now what part of my flux is changing? So I have to take the time derivative, but we know that the current is changing, right? So this derivative here, the d dt, only falls on my current, since we were told that the current is increasing. So d phi dt is mu naught n di dt, and then times that 4 times 10 to the negative 4. So let me write this on the next page. So this is our change in flux. And our di dt, we said, was increasing at a rate of 100 amps per second. So I can just now plug in all of my numbers here since I have all of these numbers. So again, I'm ignoring the negative sign for a second. We'll figure out the direction later. So the EMF is just mu naught, and then N was 500 turns per meter. Di dt was 100, and the area was 4 times 10 to the negative 4. And so this comes out to 25 times 10 to the negative 6 volts. So this is the magnitude of my EMF. And now I want to figure out what direction that EMF is in. So the direction that will have an induced current in this wire, if I know that the current is increasing in my solenoid, as I increase my current, that's going to increase my magnetic field, right? Because we said that the magnetic field for a solenoid was given by this. So obviously if I increase I, that will increase B as well, since mu and N aren't changing. So my magnetic field is increasing in this direction. So B is increasing in this direction. That means that my wire is going to want to induce a magnetic field in the opposite direction. It wants to try to keep that magnetic field, the flux through it, the same. So it's going to want to induce an opposing magnetic field. So we're going to want to induce a magnetic field in that direction, to the left. So in order to induce a magnetic field to the left, I can use my right-hand rule and say, okay, well, if my thumb is going to the left, that means I'm going to have a current that is sort of like going into the page at the top and out of the page at the bottom. So that's this direction. So my EMF that I induce is going to be in that direction. So we can sort of call that counterclockwise. So that's the magnitude and direction of my induced EMF now. And then we wanted to find the magnitude of the induced electric field within the loop if this wire loop's radius is 2 centimeters. So now that we found the EMF, we can use our Maxwell's equation to find the electric field in this wire here. So we're going to need, we said our EMF was equal to E dot dl, and we said that the electric field is constant inside that loop, so all we have to do is just multiply by the length of the path, which is just the circumference of this wire. So that will just be 2 pi r. And we said that r, they tell us, is 2 centimeters. So this is just 2 centimeters. So we have our EMF is just equal to E times 2 pi times 0.02 meters. And then we can just solve for E. So, or capital E, electric field E. So that just becomes the EMF divided by 2 pi divided by 0.02. So the EMF we said was 25 times 10 to the negative 6. And then we have 2 pi, and then we have 0.02. So this comes out to, our electric field is 2 times 10 to the 4 volts per meter. And this is the magnitude of our electric field that's induced now in that wire. And we know the direction since we know it's going to be in the same direction as the current and the same direction as the EMF. Okay, so that's it for today. We're going to do more examples tomorrow. We're going to see how a changing electric field can induce a magnetic field, and just do a lot more examples since I know this stuff is pretty confusing. So we'll do a lot more examples tomorrow, and then that will be the end of our content for the class. Okay, so we'll see you guys next time.